been a lot of questions about when to use which formulas, so I've created this little PowerPoint to maybe help answer some of those questions. The first thing to keep in mind is that what we're doing in this part of the statistics course, and one of the biggest goals in statistics, is to learn some information about population parameters. We want to know things like, what is the actual percentage of Republicans in Utah? What's the actual percentage of USU students who are seniors? What's the actual average age of all of the people who live in Washington County, or the actual average income of dentists in Weber County? Now, some of these, maybe it's not so hard to do, like the actual percentage of USU students who are seniors. All of that information exists in a database, and you could find that number out exactly. But some of these other numbers are more difficult. Contacting every person in Washington County and asking them how old they are, that would be a huge task and very expensive. So what we do instead is select a sample from the population that we're interested in. We calculate that number for the sample, and then we use information about the sample size and the sample we've collected to tell us something about that parameter that we're interested in. So keep in mind what it is that we're looking for. The population percentage, which we've been calling the EV%, and the population average, which we've been equating with the EV average, the expected value. Now, the central limit theorem tells us that the histogram of the sample percentage or the sample average will look like the normal curve and will be centered at that parameter that we're interested in. And that's true no matter what our original data looks like. So our original data can come from a 0, 1 box, which certainly doesn't look like a normal curve, or it can come from data that has a long right tail or a long left tail, all kinds of different shapes of the data. But when we talk about taking sample percentages or sample averages, and we construct a histogram of the sample averages or the sample percentages, we get this nice histogram centered at that expected value, centered at the parameter that we're interested in. Now, the shape or the spread of the normal curve depends on how large the sample size is, and we've been calling that the number of draws from the box. When we have a lot of draws from the box, our standard error for both the percent and the average goes down, and it gives us a narrower curve, less spread in that normal curve, and we call that more accurate. When we have a small sample, the SE for the percent and the SE for the average, those numbers are a little bit bigger. We have a wider curve, and we call that less accurate. So larger samples give us more accurate estimates for those parameters that we're looking for. The spread, that's the width of the normal curve, we measure that using the standard error. So when we're talking about percentages, we're going to be constructing a normal curve that's centered at the expected value for the percentage, and the width of that normal curve is going to be determined by the standard error for the percentage. And the same thing for the average. The normal curve would be centered at the expected value and then have a width determined by the SE for the average. So to find those, we need the size of the sample. Like I said, we've been calling that the number of draws. Now, we've done this from two directions. In Chapter 20 and the first part of Chapter 23, we've talked about it from the position of knowing what that parameter was. So we have a box model, we know what the population looks like, we construct the box, and we calculate the SD of the box by taking the proportion of tickets that are ones and multiplying that to the proportion that are zeros. That gives us the SD of the box, and then we use this formula here at the bottom for the SE% to give us the width of that normal curve centered around the expected value for the percentage. We did the same kind of thing with the SE average. where we use the SD of the population, and most often that number is told to you. So you don't have to use that formula to calculate the SD of the box because you've already been told the SD of the box. And in this case, you can go straight to the calculation for the SE for the average and use this formula here. Now when we got to chapter 21 and the end part of chapter 23, we're going backwards. We're saying we don't know what that parameter is, and so we're going to take our simple random sample and try to estimate it. And we use the sample percentage or the sample average to help estimate the expected values. Now these might not be really great estimates depending on the sample size. So we calculate the SE to tell us how good the estimate might be. And we use that SE number to calculate the confidence interval. Now it turns out that the sample SD is usually very close to the population SD. And this is the whole idea of a bootstrap, that we don't know the population SD, but it turns out that our sample SD does a really good job of estimating that population SD. So we use the information we've got to get an estimate for the standard error, both in the case where we're talking about percentages, where we're going to use the sample percentage as that proportion in the SD box calculation, and then use that SD box estimate to calculate the SE percent. We do the same kind of thing with the SE average. We're going to use the SD of the sample and use that in the formula to calculate the SE for the average, and that gives us again a really good estimate for the standard error. So in the end, what we do is take that sample percentage of Republicans from our sample, or the dentists from Weber County that we use in our sample. We take that sample statistic and we add Z, a Z value, times the SE for the percent if we're talking about percentages, or the SE for the average if we're talking about averages. We add that to our estimate to create this confidence interval that usually will include the population parameter that we were interested in. Now the value you choose for Z is determined by the confidence level that you want. So if you want to be 95% sure that your interval includes the parameter, you use a Z value that gives you an area close to 95%. In this case, that's 2. If you want 99% confidence, meaning 99% of the time your interval will include that parameter, then you would use more SEs. You'd go 2.6 SEs out from your sample estimate. If you don't need to be quite so confident and you decide to use a 90% confidence interval, then you would use a Z value of 1.65. And you can find other values as well using the normal table chart at the back of the book. And here's a picture of it. What you want to do is determine the level of accuracy or confidence that you want. So for instance, if I want a 90% confidence interval, I use a Z value of 1.65. If I want a 95% confidence interval, I would use a Z value of 2, and so on and so forth. If I wanted an 85% confidence interval, I could use a Z value of 1.45. And you can pretty much choose whatever level of confidence that you want. Again, the most common ones are 90%, 95%, and 99%. But the table is really helpful in allowing us to choose whatever level of confidence that we want. So hopefully that helped. If you've got more questions, please go ahead and ask in either office hours or on the message boards.